So I want to explore the idea of returns to scale in a particular, using a particular production function here. And to do this analysis, we're going to be using some of the exponent rules identified in another video. Also, we're going to be using the idea of constant returns to scale, meaning that if I double all inputs, I would double the output, or increasing returns to scale, where if I doubled the inputs, I would more than double the output, or decreasing returns to scale, when I double all inputs, I get less than double the output. And I'm going to do this in the context of a Cobb Douglas production function, which I've also described in a different video, that has this formulation where the output y is going to be equal to some constant a multiplied times the capital usage raised to the alpha power multiplied times labor to the beta power. Now, you're not going to really use these in an explicit sense in terms of calculating the output in many classes at all, but I want you to understand how the Cobb Douglas production function can be interpreted in terms of constant increasing returns to scale depending on the value of alpha and beta. And to do that, I'm going to use some exponent rules that we've described in a separate video, and specific forms of the Cobb Douglas function, and evaluate whether or not, what we can say about the returns to scale. So let's take the first one, and I want to call y0, the original level of output, is going to be a multiplied times k to the 0.5 power multiplied times labor to the 0.5 power. And in order to evaluate the returns to scale, we want to double all of the inputs, the capital and labor, using this formula, using these rules, and see whether or not we have more or less the same than doubling the output. Okay, so we'll double the inputs. So we're going to have twice as much capital raised to the 0.5 power, multiplied times twice the labor raised to the 0.5 power. And now we're going to start using these exponent rules, because that's really critical to this formulation. Okay, so what's going on over here? Well, we have two things multiplied by each other raised to a common power. So this rule number 3 seems to be relevant. So what I'm getting is a times 2 raised to the 0.5 power multiplied times k to the 0.5 power multiplied 2 to the 0.5 power multiplied times L to the 0.5 power. Okay, so I've just used this last one. Now I want to combine terms, so I can rewrite this as a multiplied times 2 to the 0.5, 2 to the 0.5, k to the 0.5, L to the 0.5. Okay, so we've just rearranged things. Now, this part right here is, you can use this relationship. It is the same base to different powers, where A basically takes the role of 2, Okay, so you then have a times 2 to the first power, that's 0.5 times plus 0.5, k to the 0.5, L to the 0.5. So what are we left with? A times 2 to the first, which is equal to the base. That's 2, or A, times 2. At this, in fact, let's even write this more easily. That is 2, I'm pulling the 2 out, multiplied times A, k to the 0.5, L to the 0.5. In other words, it's twice y to the 0. Now let me back up. Y to the 0 is the original amount of output. This next expression is when we double the capital, double the labor. And I go through this series of manipulations to get that if we double both the inputs, we're getting twice the original level of output. In other words, when the exponents add up to 1, we're going to have constant returns to scale technology with a Cobb Douglas function. Now you can do exactly this same thing with these other two versions of the production function. Just follow exactly the same steps where you're going to get a different sum of the exponents down here. So for example, 0.4 plus 0.7 would be 1.1 instead of 1. The bottom line with this is the following. If we have a Cobb Douglas function of this form, you can show that if alpha plus beta is equal to 1, and I should say that alpha is always going to be between 0 and 1, beta is going to be between 0 and 1 in anything that you might do. If alpha plus beta is equal to 1, constant returns to scale. You can show if alpha plus beta greater than 1, increasing returns to scale. Alpha plus beta less than 1, decreasing returns to scale. And I would urge you to do the steps that I talked about just a moment ago using these exponents, and you'll see that you get that exact result. So again, you're less likely to have to calculate the returns to scale than knowing this part. But I want you to not just take it on faith, but to see it in practice. And that's what I just did.